Alright, so today we are going to cover nuclear chemistry. We're going to learn about describing the process of alpha decay, beta decay, and gamma emissions, and we're going to learn how to write balanced nuclear equations. In our next lesson, we will understand, compare, and contrast fission and fusion reactions. But for right now, we're just going to cover the first bullet point. So, radioactive decay is the emission of radiation from an unstable nucleus. All elements more than 83 protons are radioactive. Nuclear radiation is the electromagnetic radiation or particles released during radioactive decay from an unstable nucleus. And we've got a couple of different types of nuclear radiation. We've got alpha, beta, and gamma, and we're going to dive more into that here in a second. So, we balance nuclear equations, and these represent the decay process of an unstable isotope. The sum of the mass of the reactants will always equal the sum of the mass number of the products. So I know some of you have guided notes, and there's a little equal sign. Mass number of the reactants equals mass number of the products. And then the sum of the nuclear charges of the reactants will always be equal to the sum of the nuclear charges of the products. So this is your next equal. So nuclear charges of the reactants equal nuclear charges of the products. So, a great example of a balanced chemical equation or nuclear equation is below, and we can see the beta decay of carbon-14. We have carbon-14 in its isotopic notation, and we can see that is our reactant. So reactant, I'm going to point to in red. And then my products, I'll point to it, or I'll underline in blue. Our reactants equal products. We've got 14, our mass number 14 on carbon and 14 on nitrogen. Carbon has a +6 on their protons, and then on the product side, we've got the 7 - 1, which is 6. So, we can see 3 different decay types, and this table will summarize the most important characteristics of each type of these decays. So alpha decay emits a particle that is a helium neutron or nucleus. It has 4 as its mass number and 2 as its atomic number. It has a mass of 4 AMU, and it doesn't penetrate through a lot. It typically is stopped by a piece of paper. The change in atomic number when emitted the atomic number of the isotope is going to decrease by 2, and the mass number will decrease by 4 due to the loss of 2 protons and 2 neutrons. Beta decay, right, the proton or the particle emitted is going to be a beta particle. That's what that fancy B with a tail means, just means beta. It has 1 in 2,000th AMU mass change, which means it loses about an electron. It has a medium penetration, and it will increase the atomic number by 1, so it'll take it from 1 proton to another number of protons, so carbon to nitrogen. There is no change in mass number, and that's because it changes a neutron into a proton. And then finally, gamma emissions, right? Our particle emitted is a gamma particle, and that's what the 0, Y, that fancy little Y is the gamma. It's the Greek symbol for gamma. It has no mass, and it's a highly penetrated substance. So it will penetrate through most things. It's only typically stopped by about 10 centimeters of lead. There's no change in the atomic number, no change in the mass number, and there's no change in the nucleus. So it just emits a high frequency gamma emission, and there's no change to that atom at all. So there are several types of radiation that can be emitted during radioactive decay, and the main type is nuclear radiation, and we've already written the definition for this, so you don't have to rewrite it. The nuclear radiation is the electromagnetic radiation or particles released during radioactive decay from an unstable nucleus. Alpha particles are one example of nuclear radiation. Then we have beta particles and gamma radiation. So the first type of particle we're going to talk about is alpha particles. And alpha particles are the largest of these particles. An alpha particle is comprised of 2 neutrons and 2 protons, giving it a mass number of 4 and a nuclear charge of +2. It has a similar or the same makeup as a helium nucleus. Since protons and neutrons each have a mass about 1 atomic mass unit, an alpha particle has a total mass of about 4 atomic mass units. Alpha particles are often symbolized by using an isotopic notation of the helium nucleus, 4,2He, or a lowercase a, Greek letter alpha, right? So alpha radiation occurs when an alpha particle is released from an unstable nucleus. For example, polonium-21 undergoes alpha decay to become lead-7. Alpha decay removes 2 neutrons and 2 protons, resulting in a stable isotope of lead, being lead-207, in a helium nucleus. A beta particle is an emitted electron, and therefore has a negative charge of 1. Beta particles have a mass number of 0 since they contain no protons or no neutrons. Oops, I went too far on my little note screen. The mass of an electron is much less than a proton or a neutron and is about 1 2,000ths of an atomic mass unit. The symbol we use for beta particles is using isotopic notation showing the mass number of 0 and the nuclear charge of -1 with the lowercase letter for beta, or B with a fancy tail. Beta radiation occurs when a beta particle is released from an unstable nucleus. For example, we saw earlier that carbon-14 undergoes beta decay and becomes nitrogen-14. Notice how the neutron to proton ratio for carbon-14 gives a value of 1.33, while nitrogen-14 gives a value of 1. Beta decay is a process that takes a neutron and a carbon atom and changes it to a proton, releasing that beta particle as a byproduct. Since the carbon and nitrogen are small atoms, it makes sense that carbon-14 with a neutron to proton ratio greater than 1 would decay to a product with a ratio of 1. So atoms like to hang out in a ratio of 1. So anytime we have an atom that's sitting at a neutron to proton ratio that is slightly above 1, like 1.3, it's going to most likely decay down to an element that is 1. So gamma radiation is not composed of subatomic particles like alpha and beta radiation, but instead of photons of electromagnetic radiation that is usually emitted after an alpha or a beta emission. Since gamma rays are pure energy, they have no mass and there's no charge. The gamma radiation is symbolized using isotopic notation, showing the mass, no mass, and no charge, with a lowercase Greek letter gamma or fancy Y. Gamma radiation is often omitted or left out from nuclear equations since it does not affect the mass or atomic number of an isotope. So, a negatively charged electrode attracts an alpha particle. Why do you think that is? Right? Correct. Alpha particles have a +2 charge from 2 protons. Now, a positively charged electrode is going to attract beta particles. And why do you think that is? Correct, because they have the same charge as an electron, so -1. And we know that opposites like to attract, so they're going to go to the opposite direction. Gamma radiation continues in a straight path because there is no charge. The image below shows alpha particles, beta particles, and gamma radiation changing direction towards the positive, negative poles. So, an alpha particle has the lowest ability to penetrate objects. It has large particles, it's great in mass, and it's the slowest. It's like throwing a bowling ball at a chicken wired fence. It's not going to go anywhere. It typically stops when it reaches a piece of paper. Beta particles have a greater ability to penetrate an object. This is like throwing a ping pong ball through a chicken fence. It will typically be stopped by 1/2 centimeter of lead because it's smaller than alpha particles and has less mass, therefore having a greater velocity. And then gamma radiation has the greatest ability to penetrate an object, and that's because it is the smallest. It is composed of light energy called photons, and it therefore has no mass, so it can go the farthest and the fastest. This is like throwing a marble through chicken wire. It's typically stopped by a 10 centimeter lead vest. So if you've ever had x-rays done, they lay that heavy metal or that heavy vest on you that's covered in plastic. Well, that's a lead vest, and what that does is protects your organs and the things that they don't want to take a radiograph of from radiation. Radiation can get in there and change our DNA, so we want to be able to protect the different DNA in our body. So, all types of radiation can cause damage to the human body. The severity of the damage varies based on the ability of the radiation to penetrate the body and ionizing atoms. So you can see here, right, alpha isn't going to go very far. It's going to stop on the top. Beta is going to go a little bit deeper into the skin, and then gamma is going to really cut away deep into our skin, causing some different types of radiation damage or poisoning. So now we are going to talk about the steps to balancing a nuclear equation. So the first step and the second step. The first step is write the given information in the form of a nuclear equation using variables to represent unknowns. And then we're going to create an algebraic equation from the chemical equation to solve for the unknown variables. All right, so we're gonna write a balanced nuclear equation showing the alpha decay of uranium-238. So we know that there are two steps to writing an equation, and our first step is write the given information in the form of a nuclear equation using the variables to represent unknown. So we have uranium 238. And if I look at my periodic table, which is off screen, I can see that uranium has an atomic number of 92. All right, and then we know that our alpha decay is going to be something a Z plus HE4 2. And now we can rearrange this equation and figure it out. So we know mass number equals A plus 4. So step 2. This was step 1. So our mass number is 238 equals A plus 4. To get them on the same side, I'm going to minus 4, minus 4. I'm going to have 2, 3, 8. Sorry, 2, 3, 4 equals A. So my equation, I'm going to start writing down here, 2, 3, 8, 9, 2, 2, 3, 4. And then I know that it would be atomic number minus Z equals Z plus 2. So that would be 92 equals Z plus 2. So 90 equals Z. If I go look at my periodic table, I can find that what has an atomic number of 90 is TH. For 2HE. All right, so let's have you practice one. All right, so let's write a balanced equation for the decay of iodine 31 to xenon 31. Okay, so step 1 is we're going to write an equation using numbers as variables, or variables to represent the unknown. So I know I have 131 iodine, and if I go look at my periodic table, I know that the atomic number is 53 to AZX plus 131 xenon. We found the atomic symbol to be Xe, and then the atomic number would be 54. So then we can work our algebraic equations, or create algebraic equations. to figure out our unknowns. So step 2, right? 131 equals A plus 131. So I subtract 131 from each side. 0 equals A. So I'm going to start writing my equation down here. 131/53. 131/54xe plus 0. So then I do my z. So I know 53 equals z plus 54. Subtract 54 from both sides. And I leave with a -1. And we know that 0, -1 means that it's beta decay. So I'm going to do my fancy B. Does this make sense? Perfect. Now I've got some practice problems for you to do.